Okay, welcome back, everyone. We will continue discussing how to model diffusion and implement chemical fields in CompuCell. This is now module 2.4, although we will continue with some of the exercises from the previous module. And just as a reminder, this presentation is being recorded and live streamed. So in the previous module, we talked about how to model chemical concentrations and diffusion of these chemicals using CompuCell. In this module, we will discuss how to add cells and what cells can do to these fields. They can either act as membranes, or they can secrete to and absorb from this module, from this chemical field. But before getting into that, I wanted to finish the last part of the previous module because it is important. The last part of the module we saw was the implementation of the linear gradient, right? And the way we implemented that linear gradient was by establishing a fixed value of the field in one edge of the domain and another value at the other edge of the domain, and having the molecule diffuse between one edge and the other. But in our simulations, the molecules diffuse freely without being interrupted. In reality, in biological context, and what we see is that as we implement that field and we measure in, our simulation starts with all the concentration of the chemical at one edge, but then that concentration diffuses through the domain until a equilibrium concentration is reached, where the concentration decreases linearly from one edge of the domain to the other. And this linear concentration, again, is due to the fact that the molecules are diffusing freely from one edge to the other. As a bonus, I have it in the code that I shared, the 2.3.2 code. You can also, since we solved the diffusion equation under those particular conditions, we know what the equilibrium concentration should be of the field, and then we can plot the actual concentration versus what the equilibrium concentration would be. And if we wanted to measure, for example, the time that it takes for the concentration to reach equilibrium, we could do so by, let's say, subtracting and measuring how fast the concentration profile reaches the equilibrium concentration. But that is as a bonus that I left in the code that I shared with you. Now moving on to solving the diffusion equation with decay, we need to take into consideration that in living organisms, molecules do not freely diffuse across tissues, right? They interact with other molecules that are consumed by, let's say, cells, or they undergo chemical transformation because of chemical interactions with other molecules. And the way we model the fact that this type of, that the molecules can be consumed, or that they are basically used up, is by including a decay term in our diffusion equation. And it's also important to know that this decay is gonna determine an very important biological quantity that we call the diffusion length. And the diffusion length is basically the typical distance that a molecule is able to diffuse in a particular tissue, taking into consideration that the molecule is both diffusing but also decaying. And that diffusion length depends on the particular molecule that we're talking about and the particular tissue that we're talking about. So for an example of this decay is oxygen being diffusing from the capillaries into the tissue. It has a characteristic length that the oxygen molecule can diffuse into the tissue, and this determines, usually determines, for example, the spacing, the minimum spacing necessary between two capillaries to provide appropriate oxygenation to the tissue. And so on. This diffusion length determines important time and length scales for different biological processes. So as I said, the way we can model this consumption of molecules or this exhaustion of molecules is by, or the decay of molecules is by including a decay term in our diffusion equation. So remember, our diffusion equation without decay was this first part of the equation. And now we add an additional term that is accounts for the fact that our molecules decay in the domain as well. And then it's important to notice that the decay is going to be proportional to the concentration. So the more concentration, so the initial concentration or the available concentration, and that is going to be, and then how fast it decays is going to be determined by what we call the decay constant. If we solve this equation, what we see is that instead, as in the previous case where the concentration profile changed linearly from the source, the concentration in this case with the decay term is going to decay exponentially from the source. And the exponential rate of decay is going to be determined by both the diffusion coefficient and the decay rate. And then such that the diffusion length, now we can define it mathematically, is the distance over which the concentration decreases by a factor of E. And that is usually so we can determine what the diffusion length of a molecule is by taking the square root of the diffusion coefficient over the decay rate. Biological molecules have, depending on the molecule, have typical diffusion lengths of 5 micrometers to 150 micrometers. So if we come back to the previous simulation that we were exploring, we can come back to the code that I shared in exercise 233. I'm gonna just load that one. So I would recommend everyone to do the same, to load the code that I shared, exercise 233. And some of this is gonna be familiar to us already. We can see that I'm plotting the concentration of the field at the by measuring the concentration across my simulation domain. And in the XML, I can see, Giuliano, can you please share the link to the folder where the demos are? If I come back to the XML, I should be able to see that I've specified the boundary conditions that I needed, the same boundary conditions as in the previous example, periodic on X on the Y plane and fixed value on the X plane or X axis. But now I am, instead of setting my global decay constant to 0, I am setting it to 0.01 or 0. And when I run that simulation, what I see is that instead of decreasing linearly, my chemical, the concentration profile decays exponentially from the source. So we can set the diffusion. I showed the example where I set the diffusion, the decay constant directly into my XML, but I can also, for those of you who have been able to use it, I can also do it using my model editor. If I go to the steppable tab, the diffusion field tab, and the diffusion data tab, now I have the global diffusion coefficient and the global decay constant. If I set that decay constant to 0, I am again in the domain where I have a linear profile, concentration profile. And again, how fast does it take to equilibrate depends on my diffusion coefficient. But if I set my global decay to a non-zero value, then my profile is gonna decay exponentially instead. Okay. And let me share the poll to make sure that everyone is with me. And then you can play with this simulation yourself. You can see, okay, what happens if my decay constant is small? Then the smaller my decay constant is, the closer my concentration profile is to the linear case. And then the bigger it is, the faster the exponential decay of my concentration profile. And then again, how fast does it take to get to the equilibrium concentration? It's gonna depend on the diffusion coefficient. And note that, of course, because the diffusion length is determined both by the diffusion coefficient and the decay coefficient, when my decay coefficient is not 0, the profile is also, the equilibrium profile is also determined by what my global diffusion coefficient is. Stephen, I can show my code again. It's just the same code as before, except that we've set the global decay constant to a no 0 value. In this particular example, I set it to 0.1. Okay, cool. So, so I'm gonna leave this code to you to play, to get some familiarity with the idea. Again, if you're able to use the model editor, I would recommend you playing with these values and understand how they control what the profile, look at two things, right? What the equilibrium concentration is, and then how fast it takes for the profile, for the concentration to reach that equilibrium state. So I'm gonna show the code for those of you who need a little bit more of time. I'm gonna give you, if you checked on needing more time but finished the exercise, please do check on yes, so I can get a sense of how many people are finishing the exercise.
People can't change their vote, so we have to relaunch the poll.
Oh, so okay. Well, so I'm okay, good. So I'm gonna yeah, I'm gonna assume most people have finished already. So, but again, you can build on the previous code. Okay, good. Yeah. So I will continue on then. So as a bonus, I added additional code in the code that I shared with you. I added a line that shows what the value is when the original concentration decays by a factor of E, right? And I added a line that measures at what distance that concentration has decayed by a factor of E, which is gonna basically determine what your diffusion diffusion length is. And notice that this is just for the particular example where my diffusion coefficient is 1 and my decay constant is e⁻⁻1. If I change those, then I would have to come to this code and readjust those values to see what the actual diffusion length is for different values of those parameters. Okay, so let's continue then with the material for module 2.4. This is the second part of the chemical fields presentation. And here I will be discussing how to use cells to specify diffusion coefficients that vary at different locations of the simulation domain. So in our previous examples, we assumed that the diffusion coefficient was uniform in all of our simulation domain, but we are also able to set varying or local diffusion coefficients, and we do that by introducing cells into our simulation domain. Then I will show another way cells can interact with the field is by secreting some of the chemicals to the field, and also by absorbing from those fields. And I'm gonna show you examples of how those can be implemented and how they affect the concentration profile. So again, in real biology, the particles do not diffuse equally across the same let's say biological domain or the same space, because the space is usually occupied by different let's say there's areas where there's higher density of certain types of molecules, or there is actual barriers that prevent cells from moving through certain areas, or cells in it or molecules interact more or less with other molecules at different regions of the space. So that will effectively, if from the standpoint of modeling transport as diffusion, that would effectively be modeled as a diffusion coefficient that varies spatially. So in terms of how the diffusion equation is how we can mathematically represent that in the diffusion equation, in this particular case, our diffusion constant is now a function of the particular location I'm looking at. The diffusion equation becomes a little bit more complicated but we can neglect this term if we this third term if we assume that the differences in concentrations, I'm sorry, if the differences or the changes in the diffusion coefficient are not too big. So we'll stay with this last part of the diffusion equation, which basically states that the diffusion coefficient, the change in concentration depends on what the value of the diffusion coefficient is at that particular location and the gradient of the concentration. And as I said, the way we implement this in CompuCell is by specifying cells and then specifying what the diffusion coefficient is inside of those cells. So to exemplify this, we will continue building up upon what the examples we were showing earlier, but we will introduce cells that will basically function as a membrane the chemical can diffuse through. So the idea is that, again, we will create a simulation with a single field and a single frozen cell type, and then we will use a uniform initializer to draw a membrane in the middle of the simulation domain. And Giuliano earlier today showed a bit of how to use a uniform initializer to draw cells. And then we will set a different constant local diffusion coefficient inside the cell, the membrane cell type, to make the membrane semi-permeable or to make the membrane impermeable. And then as a bonus, we will open a channel through this membrane and look at how diffusion changes if it's diffusing through a channel in a membrane. So let's do this together. We will create a new simulation. I'm gonna call it membrane. And again, I'm gonna do it, although it says 200 there, the examples are 100 by 100. So I'm gonna type it here. It's 100. Now I am actually gonna be using cells, but since they are gonna be frozen, they're not gonna be moving. I don't necessarily care about what happens at the boundaries because my cells are not gonna be crossing any boundaries because I'm gonna freeze them. Now I do have to introduce a cell type, and I'm gonna call it membrane. And here I can check to have our cells frozen, and that, again, that means our cells are not gonna move. Let me make sure that my chat is. Hit continue, and then I can add. Yes, I can go back here to the cell type specification.
Another one.
Okay, to the simulation properties. So all I did was I specified a 100 by 100 simulation domain. And then I added a membrane cell type. And it's frozen. And then now I'm gonna add an oxygen chemical field. Again, I keep calling this oxygen, but you can call it as you please, and depending on what molecules of interest you model. And then although I have cells, since they are frozen, I do not have to activate any of the cell properties or behaviors because my cells are basically they're gonna be placed there, but they're not gonna be moving or doing anything except serving as a barrier for diffusion. Then I can finish my simulation. I can finish my I can finish the wizard, and then I can come to my XML file. First, I check that I've added my cell type membrane, that it's frozen, and this tag indicates that my cell is frozen. And now I can see that I have additional information in my diffusion solver steppable. I have the global and diffusion parameters, but I also have the diffusion and decay parameters that are specified by cell. And this is where I can change what the diffusion is inside of cells belonging to this membrane cell type. For this particular simulation, I want no decay. So I'm gonna set my global decay constant to 0. And I'm gonna, and my local, or my decay coefficient inside the cell, I'm gonna also set it to 0. No, sorry. And the diffusion inside my cell, I'm gonna make it 1e to the minus 5. Okay, and I want the linear gradient again. So what I'll do is I'll set the value, a constant value of 10 in the minimum of the y-axis and 0 on the maximum of the y-axis. And I want periodic boundary conditions on the y-axis. To initialize my cell membrane, I use this uniform initializer. And what I'll do is I'll set it basically in the middle of my X domain, going from 45 to 55, all the way from the bottom of my Y domain to the top of my Y domain. Okay. So I'm gonna pull and relaunch just to make sure that everyone's caught up, because this sets up everything for this particular exercise. So again, I have a global diffusion coefficient that I set to, let's set it to, actually to 1. A global decay constant that I'm setting to 0 because I want the linear gradient. And then I am making the diffusion coefficient inside my membrane to be 1e to the minus 5. Decay inside to be 0. And then I set the linear gradient by having constant values on the x-axis, periodic on the y-axis. And then I initialize my membrane by specifying the regions in which my cells are gonna be created. It's gonna be from X position 45 to X position 55. So that's basically the center. And in Y to 0, from 0 to 100. Now, if I execute that simulation, First, I should see the membrane in the middle of my domain. And then I'm gonna open another window so I can see the field. And I want someone to execute them on their end and tell me what they see before I run it on mine. Right. So, but what happens when it reaches the cells? What happens to the fields when it reaches the cells? Right, it accumulates, and that is because it's the membrane I created is semi-permeable. So even though the chemical can diffuse through my membrane, it diffuses slower. So you would see that the chemical field can get through that membrane, and I'm gonna execute it now. Sorry, I'm sorry, I forgot. There is this, once you created a cell field, the steppable automatically sets your cell type to secrete to that field. And we don't want that right now. So everyone will need to come back to their XML code and comment this in secretion data. Please comment out this secretion tag. So actually, in this particular case, to comment, I set, right, you can set secretion to 0 or you can comment it out. Those are equivalent. If you want commented out, you place your cursor on the tag, then you can come to file, to edit, and you can save, and you can hit in block comment. So in this particular example, the diffusion coefficient is so small inside my cells that basically the chemical field is unable to diffuse through it. So let's increase the diffusion coefficient to be 0.01 instead. And you see that it's still diffusing through the cell field, but very, very slowly. Now let's set it to a 10-fold slower or 10-fold smaller diffusion coefficient. And now you can see that it's coming through the membrane, but when it gets to the membrane, it slows down. Once it's past the membrane, it diffuses again faster as before crossing the membrane. So if you want to slow it down, you basically decrease the diffusion coefficient on the cell type membrane. So in this case, this is a semi-permeable membrane, right? The chemical diffuses through the membrane, but it diffuses slower than in the outside. If I make it very small, then I make my diffusion, then I'm effectively making my membrane impermeable. So it's coming through this edge, but it cannot cross this membrane. Joseph, make sure that your field properties are fixed. Again, because the visualization of the field is gonna be dependent on what your visualization options are. So in my particular case, I have them fixed from 0 to 10. It also depends on what your diffusion constant might be. If your diffusion constant is very fast, then it's gonna fill in the space. So that is an excellent question, Farnoosh. Yes, that is an option. That is an option. We can we can make ourselves consume from the field. We also have other more active ways of doing it with where you have more options as to specify how the cells consume from the field. And I'll have examples after this one. But yes, that's an option. Okay, so let me, relaunch and make sure that everyone's with me. So again, I can always play with I can always play with the parameters of my diffusion by coming to the model editor. And then now I have both the global and diffusion global diffusion and decay coefficients, but I also have the local decay and diffusion coefficient. So I can set it, let's say, to the same as the field, as outside of the membrane, in which case the chemical acts as if there were no cells in the simulation domain. Or I can decrease the diffusion through the membrane, or I can make it impermeable by setting the diffusion to 0 inside in my cells. So in this particular case, since I already had some chemical inside the membrane, when I change it to 0, that chemical is just going to remain there. That's it. Aaron, that is an excellent question, and I'm actually not sure. Maybe TJ or Giuliano can probably answer that question better. TJ, do you know?
So the global decay is applied everywhere that does not have any other specification. So if you specify a decay coefficient for a particular cell type, that specification for that type will override or supersede the global decay constant, and that's also true for the diffusion coefficient. So the global values are the de facto value for everything that doesn't have any other specification.
Yeah, so it's not additive.
Correct.
Okay, so I'm gonna, most people are caught up with me here. So I'm gonna continue because the next parts are also important, but just as a right, this is exactly what I showed already. Oh, I can also plot, right, add the plots. to see what how the concentration is changing. The plot is the plot code. This is why I wanted to spend some time of it on the last section, because it's basically universal, so we can just copy it and paste from the previous simulation. And I don't need this, but I need the basic one. But I'm measuring the concentration. I'm creating the plot window, and then I'm measuring the concentration. And if I just copy and paste that into this, then I can see into this simulation, then I can see into the stepables of this simulation, then I get my code. And this is what we'll do, because we'll get the plots for all of the next couple of simulations. Okay. Good. So, and as a reminder, you can find examples of this code in this folder in the Google Drive, and this will be exercise 21241. And then you can play with the permeability of the membrane. And this is just as a teaser. I'm gonna leave it as a homework, but we can, by playing with the initializer, we can open a channel in our membrane and then see how that changes the diffusion of our chemical. And these are examples of diffusion through, in this particular case, the membrane is impermeable, but I open a channel that it's that lets the chemical diffuse through. So important here is that as it approaches, remember that the contour plots show the regions of the domain where the chemical concentration is the same. And you can see that inside the channel, the chemical basically diffuses more or less linearly. And then outside, it has this curved shape until it's far away where it diffuses linearly again. But this code is also available for you in that 2.4.1. It's just commented out for the purpose of this exercise. But I'm gonna leave it as an exercise to you to play with the width of this channel and see how that changes the diffusion of the chemical. So another way cells can interact with the chemical fields is by secreting molecules to that chemical field. Cells do secrete biological molecules. They have different ways of secreting these molecules. From our standpoint, we neglect the details of the specific secretion mechanism, but the main idea or the biological idea the main idea behind the secretion is that the net effect of the cell secreting particles is that the concentration above the, let's say, apical surface of the cell the concentration of that chemical increases as the cell secretes more and more of that chemical. From the modeling perspective, we can model secretion by adding an additional term to our diffusion equation, and this is what we call a source term. And in particular, the source term is gonna be dependent on the cell that occupies that particular location. So now our diffusion equation is going to be, so the concentration at a particular location is going to be determined by the gradient, the diffusion coefficient, the decay, but also how much is being secreted into that particular domain by the cells that are, let's say, directly beneath it. So CompuCell has many different ways in which we can implement secretion. So the idea again is that we have a special plugin that allows that facilitates or enable our cells to secrete an uptake from a particular field. And then we specify the rate or the specific format or the form that we want our secretion to have. There's two ways we can specify secretion in CompuCell. We can either do it directly in the XML, or though our options are a bit limited in that particular case. Or we can do it in the Python steppable, which gives us much more control over the type of secretion that we want to have. And this is going to be the same for uptake of absorption. So if some of the options that we have to implement secretion is that we can secrete at the boundary of the cell, inside the cell at the boundary. We can also have secretion happen at the boundary of the cell, but instead of inside the cell, at the outside of the cell. And we can have secretion also happen inside the cell over every pixel that the cell occupies. Or we can have secretion happen at the center of mass of the cell. Another option that we have that is commonly used, especially in some of our modeling papers, is that we can have medium become a source of the chemical by having medium secrete. Even though medium is not a particular cell type, it's not a cell type that has the properties of other types of cells in CompuCell. Secretion is something that our medium can actually do. And the advantage of having secretion done by medium is that we can control much easier what the equilibrium concentration of the chemical is in our simulation domain. And this is what we're gonna do now. So mathematically, if we think about it from a mathematical standpoint, the equilibrium, what the equilibrium concentration is, once we have uptake and decay, it's gonna be the ratio of the uptake rate over the decay rate. And to prove that, we will create a simulation domain. We will add an oxygen field, and then we will enable the secretion plugin and specify the secretion rate of medium to be some particular value, and see what the equilibrium concentration is that we reach in the simulation domain. So let's do that together. I'm gonna create a new simulation. I'm gonna call it secreting medium Again, I'm gonna make it 100 by 100. I won't have cells in this particular simulation, so I don't care about the details, the other details. Again, I have no cells in this particular simulation. I add the oxygen field. And now here, I do have to enable the secretion plugin. And then once I enable my secretion plugin, I get this additional tab. Usually by hitting continue in this previous section, I will complete no cells. I will complete my simulation specifications. But now that I have enabled the secretion plugin, that allows me to specify that it gives me this additional tab to specify the secretion options. And what I'll do is I'll specify the secretion of oxygen by medium as a uniform secretion at a uniform constant rate of 0.2. I add as an entry. And then I finish my simulation. So now I can come to my XML. Let me launch this. And then in my XML, we're going to use this as a template. So what I'll do is as we can notice, since we enabled the plugin step, now the secretion plugin, now I have this additional plugin information here in the XML. But that same information I can also specify in the secretion data in the diffusion solver step. And I prefer doing it there because that way I ensure that the secretion and diffusion are implemented at the same time, rather than one being implemented before the other one. So what I'll do in this particular case is that I'm gonna delete the information in this secretion plugin, but not the plugin itself. Just gonna delete this information. And I'm gonna specify it again here in the secretion data. Before deleting, just copy this secretion information. Paste it in the secretion data in the steppable, inside the steppable, and then now you can comment out or delete the specifications inside the secretion plugin. Okay, now I'm gonna specify my diffusion constant to be 0.01 and my decay constant to be 0.001. So yeah, in the secretion plugin, I commented out the information here that has the field name, the secretion type, these tags over here, and I basically moved them inside the secretion data. And then I'm gonna specify also my boundary conditions to be periodic on the X and Y axis. And always remember, remove the uniform initializer because we're not gonna have any cells. Let me try running it up. Before you run it, let me make sure that I have the right syntax. Okay, so that's not the right syntax because my medium is not secreting. I did upload a copy of this particular exercise as well. This is just as a reference. So if this happens to you as well, this is why we uploaded this information. Okay, so it's just right because we already have the field, so we don't need this field name data here. So we just not need to specify the secretion. Okay, so that should work. I'm gonna stop. I'm gonna relaunch the poll just to make sure that everyone is with me. So as a reminder, I commented out the secretion information in the plugin, and I added this line in the secretion inside the secretion data. And then change the diffusion parameters and my boundary conditions. Okay. Next thing I'm gonna do is that I'll add the plot code that I've shared, that I've been using repeatedly, and I'm just gonna put it in the steppable. So I just have to override my start and step function. So quick question, based on these numbers, what should the equilibrium concentration be based on solving the diffusion equation here? So I'm gonna show the numbers again. So my secretion rate is 0.1, my decay rate is 0.01, and my diffusion coefficient is 0.1. Right. So my equilibrium concentration should be 10 based on how much the medium is secreting, but how much is also decaying. So if I run that simulation, what I should see, oh, so yeah, 1 second. Let's see if it's a matter of, yeah, hold on. .1 and it's, I'm sorry, it's 0.0. Okay, now I have the right. Right, so my equilibrium concentration should be 10. Oh, I'm sorry. That's not what I wanted to do. I wanted to share my relaunch the poll. So I want everyone to be with me here. So again, the reason I'm reaching this equilibrium concentration is because my medium is secreting the chemical. And once the medium secretes this chemical, the chemical decays based on the rate that I specified. And then the equilibrium concentration that my field is going to reach is going to be the secretion rate over the decay rate. Okay. So I'm gonna give people a couple of minutes so they can catch up. Remember, all I did was I specified my secretion plugin, but I moved the information out of this secretion plugin and put it inside my diffusion step-out. And I did specify my global diffusion constant, my global decay constant, my secretion rate, and then my periodic boundary conditions on the X and Y axis. And notice that the equilibrium concentration does not depend on what the diffusion coefficient is. Gonna give people 2 or 3 minutes. Again, if you want to get if you want to have this code as a reference, the name is exercise 242. Okay. Okay, let's continue with the next example. So now what we will do is we will introduce a single cell, and then we will explore what the different secretion options are, and how the concentration profile changes depending on the options that I choose. So what I'll do is I'll build this full simulation with all the possible options, and then we will explore each option independently. Okay, so I'll start by creating, again, a new simulation. I'm gonna call it single source. And I'm changing it to 100 by 100. And in this particular case, the cell is also going to be frozen, so I do not care. And the reason I'm doing all of this with frozen cells is because then the concentration profile is static, and we can actually actually focus on the effect of the interaction between cells and fields, rather than also taking into consideration the cell movement. So I'm just going to call my cell type cell and make sure that it's frozen. Oh, sorry. So how to plot again? I'm sorry. I didn't see those comments. So I'm basically using this default plotting code that I'm pasting in the chat. But again, to generate this plot, I use the pull down menu options and the options on scientific plots. I set up the window and the data series by choosing this option on the start function. And that's how I created these 2 lines. And then I added data points to the plot by using the pull down menu, scientific plots, add data points inside the step function. And that's how I get this line. And then I measured the concentration of the field by getting this field reference from my pull down menu, chemical field manipulation, and I needed two things. I needed the reference, which is a way for my Python to reference the field that I create, that it's specified in the XML, and then the field value. And this is what this line and these lines are. And what I'm doing is I'm iterating on my X domain to get the value of the field at each position in the X domain, and in the Y domain, I'm just measuring right through the middle, and then I plot it. That's what I'm doing. Okay, so now I can come back to the simulation that I was working on. I was creating a new simulation. I was calling it single source is 100 by 100. I added a cell type and I froze it. I am also adding a chemical field again, calling it oxygen. And then I have to enable the secretion plugin. And I'm not gonna specify anything here because I'll do everything in the directly on the XML or in the Python file. Okay, let me close all of these windows. So in the XML, we have the two cell types, the medium and the cell. And then the first thing is that we're gonna create a frozen cell in the middle of the simulation domain. In this example, I use the blob initializer instead of the uniform initializer. If I wanna change the stepables once I have created the simulation, I don't have to start over. I can just, let's say, delete this, the uniform initializer stepable, and I can come to CC3DML stepables and call the blob initializer. And that's gonna paste the code that I need. And then to create one cell, I'm just gonna specify a cell of radius 8 and gap 15, and I'm sorry, width 15, gap 0. And that's gonna create a cell in the center of my simulation domain. Remember that this cell is gonna be frozen. And now there is two types of secretions that I can specify. Well, there's more, but for a cell that is just one cell, let's set my boundary to periodic on the X and Y axis. And let's set my global decay coefficient to be 0.01 and the same inside the cell. And as I was saying, there is two types of secretion that I can specify in the XML. I can specify secretion inside the cell, which is the one where every pixel of the cell is gonna secrete, or I can specify it as a constant concentration, in which case each pixel of the cell is always gonna have a constant value. And this is equivalent to the fixed and fixed value and fixed flux boundary conditions that we saw, but instead of being applied at the edge of the simulation domain, there will be applied inside the cell. So the first thing I'm gonna do is I'm gonna test the secretion inside cell. Again, I do want the plotting code. So all I'm doing is basically, because I don't wanna have to redo it for every simulation, I'm basically copying and pasting my plotting code and replacing my start and step function with that plotting code. Okay. And now let's execute that simulation. Single source. And I have my cell in the middle of the simulation domain, my measure of the field, and I can see the cell secreting. I'm gonna turn off my contours so we can focus on the colors because this is important. Okay, I'm gonna launch the poll to make sure that everyone's with me. And in this particular case, yeah, this is secreting inside the cell. So I'm gonna show the code again. Yes, absolutely. That's what I was about to show. So I did specify my diffusion parameters, the diffusion coefficient and the decay coefficient. I specified the secretion rate, and then I specified periodic boundary conditions on X and Y axis. And then for initializing my cell, I just specify a radius of 8 and a width of 15 using the blob initializer. I'm gonna give people a little bit of time. But now you can see that the cell is the one actually secreting the field. If I wanted, instead of the secretion option, I also have another secretion option where I specified the cell as having a constant concentration instead of a constant secreting rate, which is equivalent again to the constant value flux that I showed. I'm also gonna remove my fixed values. So you can see now that the concentration inside the cell is always a particular value, 1, which is the one that I specified. And I don't know why this. And then outside of the boundaries of the cell, then the chemical decays exponentially, which is expected, right? Because the cell is acting just as the boundary was acting before as the source of the chemical. So it's important to notice that the shapes here are very different, and those shapes the shape of those profiles might be very important, especially when you're in the proximity of the cell. Okay, I'm gonna continue going to show how to specify the secretion inside cells in Python. So now in this same file, what I'll do is I'm gonna comment out all the secretion options in my secretion data. And then I'm gonna come to my Python step table. And this part is important. And in the step function, again, my best friend is always gonna be the CC3D Python pull down menu. And I have a secretion uptake option. And this secretion uptake function has all of the options that I want for the different secretion options that I have to the ones that I explained at the boundary or inside the cell or outside the cell or at the center of mass. But I'm just gonna show what it looks like when you put one, because all of them are the same. So when you click on it, you get this code that you have to fill in, this code snippet that you have to fill in. You have a secretor object that you need to adapt by referencing the name of the field as is in as specified in the XML. In my case is oxygen. And then I make my cell secrete by calling this secretor.secrete inside cell method. But see that this is referencing a cell. So to be able to use this, I need to specify what cell I want the secrete inside cell function to apply. So the way I can, one of the many ways I can do it is to iterate through my list of cells, which in this case is just one cell. And then here I specify what the secretion rate is inside the cell. So again, CC3D Python, secretion, and I choose a particular option of interest. And I had to specify the field name. And I had to specify what cell this applied to by wrapping the secrete inside cell inside of a for loop. And when I execute it, now secretion is being specified in Python rather than the XML. I'm not gonna type all of the different options because I already did that. If you open Excecise (243), and you go to the Python step table option, you can see all of the options being specified there, as well as in the XML. Right, so in this particular case is specified in the XML. For if you wanna, as a homework, I'll let you play with each of those different secretion types just by commenting in and out, whichever of the secretion options is the one that you're interested in having a look at. So these are the ones specified on the XML. These are the ones specified in Python, and see that all of them produce a different type of profile. So I highly recommend, because this one would require a lot of legwork to implement each of the secreting options. I would recommend having a look at this particular example that I've shared with you. Okay, so I want to cover Uptake. At least the Uptake is implemented, basically, it's pretty much implemented in the same way as Secretion. The mathematics are a little bit different, so I'm gonna go over a couple of minutes so I can actually explain Uptake, because it's also important. But in terms of the implementation, I'll just show the code because it's not different from the code that I'm showing here. It's just that instead of secretion, it does the uptake. So cells do take up, of course, they do take up chemicals from their environment, biological molecules, and this is important for respiration. This is also, we can also think of this as, for example, when cells get infected by viruses, they do take up viruses from the environment. And there is different mechanisms by which cells take up oxygen, take up molecules from the environment. But from a modeling perspective, from CompuCell perspective, we can summarize or we can simplify those by thinking that the net effect of uptake is to reduce the concentration of the chemical in the domain of the cell. So it's important to notice that the uptake has to be proportional to the concentration, because of course, how much the cell, if there is no chemical outside of the cell, there's no chemical the cell can take up. So there always has to be, in terms of the mathematical model, we always have to do the uptake a function of how much of it is available in the outside. And we also know that there is a limit, there is a speed limit at which cells can take, at which cells can uptake from the environment. They cannot just take infinitely fast. So we have to taking those two factors into consideration. The best way to model uptake is by having a saturated function where uptake is 0, is the concentration is 0, and it has a maximum rate when the concentration is high. The way CompuCell implements this uptake is that we have to specify two parameters. We specify what the uptake rate is after a particular concentration, and below that particular concentration, what fraction of that amount it takes. So basically, it acts as a uniform absorption or sink after the concentration increases above a particular average. It takes all of it, and below that concentration, it takes proportional to the concentration that is available. And that is the way that CompuCell approximates the saturating function that needs to be used for the uptake. So when we, the semantics are, the syntax for the uptakes are the same. So uptake in CompuCell cannot be specified in XML. It has to be specified in Python. And the uptake is relatively similar to the secretion, except that now we have to specify 2 arguments instead of one. We have to specify what is the maximum uptake rate and what is the relative uptake, or how much of the or the relative uptake rate that basically indicates the fraction that it takes below when the concentration is below a certain limit. And if we want to see the implementation of this in CompuCell, we can open, because I'm not going to build the simulation from scratch, we can open exercise 244. And again, uptake is not, at least in CompuCell, uptake is not specified on the XML. It's always specified on the Python. And the options are here. Again, these options we can have access to by going to CC3D Python, Secretion, and then we have the different uptake functions inside the cell, inside cell at boundary, inside cell at center of mass, and outside cell at boundary. And I'm gonna leave it as an exercise for you to run it. But it does create different profiles, concentration profiles, depending on what uptake form you adopt. And in this particular case, I had the source of the chemical field to be from the boundary. So I set a fixed value at the boundary, but I could also do it by having the medium secrete as we did before. And the profile, the concentration profiles look very different. And this matters in terms of whether the source of the concentration or the chemical is far away from the cell, or the source of the chemical is right at the membrane or the boundary of the cell. Okay, I'm gonna stop here. I'm gonna leave this particular presentation to this particular simulation to for you as a homework to explore. But remember that then there is these 2 options where you can have either the medium secrete or you can have the boundary being the source, and then all the different options as to how the cell is secreting. And I'm gonna let James run the end of module poll now. And if you have questions, please feel free to ask them now.
I have a question regarding choosing which solver to use. Imagine that we are choosing one solver. So how should we know that the solver doesn't work correctly, or in terms of stability, or we should change the solver? What is the indication of the incorrect solver that we should change it?
Right. So so for this particular, so in this particular type of simulations that the chemical field was not interacting except with the cells, and the diffusion coefficient was relatively small, the diffusion solver is fine. The diffusion solver FE is fine. If you have very high diffusion coefficients, we recommend using the steady state diffusion solver instead, because in that particular case, the molecule diffuses so fast that it reaches the equilibrium we assume that it reaches equilibrium really fast, so we don't care about the transients. And there is the diffusion reaction diffusion solver that allows you not just to specify the diffusion of the molecule, but also whether it reacts with, for example, with a different field. Let's say you have an oxygen field and you have, let's say, a glucose field, and you want those to interact somehow between each other, then you can use the reaction diffusion solver such that the fields will interact between each other. But that's going to be dependent on the particular problem of interest. So yeah, there's of course no a priori best diffusion solver to use, except based on the particular problem that you're interested in. AJ, you have a question?
In the wizard panel, there was a choice for enable multiple calls for PDE solvers. What was that? When we were choosing the diffusion solver.
Right. I think TJ can explain that a bit better.
Okay, I can jump in. So the diffusion method we use is numerically unstable for large diffusion constants. And the original version of the diffusion solver, you had to explicitly tell it if you were going to use a large diffusion constant, and then it would know that it should actually call the diffusion solver multiple times per step. That's now done automatically. And so you don't actually need to use that button for your diffusion constant. It winds up that it's possible that if you set the decay constant to be very large, you can get numerical instabilities, and then you have to play with things a little bit. CompuCell does allow some games where, in general, this concept of a Monte Carlo step is the smallest time step that steppables are called in. It's possible to actually sub-step them models if you need to. I wouldn't worry about those kind of things until you need them. There are going to be a lot of options within CompuCell that we're not going to mention typically because you don't need them. And so if you leave them set the way they are, you should be okay. But it's true that there are a lot of options. And so by all means ask. In this case, that's essentially a legacy option because we wanted to be able to allow old code to continue to run. But you shouldn't have to click that box.